Hey everybody, welcome to 12.5 Probabilities of Independent and Dependent Events. So I want to just remind you, we learned in 12.4 about something called a compound event. And a compound event was when you only are doing a single card draw or a single dice roll or a single coin flip or something like that, but you're happy with two different outcomes. So for example, if I drew a card, I'd be happy with a king or a queen. That was a compound event that we learned in 12.4. In 12.5, we're talking about multiple events. So what I mean is we're going to find probabilities such as, what's the probability of me drawing a queen and then drawing a king? And I'm going to draw actually two cards out of the deck. So multiple events. And yesterday when you learned about 12.4 with the compound events and you added the probability every time, when you have multiple events, you are going to multiply the probability. So here are our two little formulas. But first I want to tell you what independent and dependent events are. So independent events. The official definition of an independent event is that the occurrence of one event has no effect on the other. The occurrence of one event has no effect on the other event. What I mean is, let's say that I did flip a coin. I flip a coin, and then I flip a coin again. The second event has nothing to do with what happened in the first event, so that would be considered independent. Or maybe I am going to roll my dice, and then I'm going to roll my dice again. Those are independent events because they don't affect each other. And here's our formula. I'm going to do the probability of A and then B, and that is the probability of A times the probability of B. And now I want to specifically do this because this is one thing I dislike about these formulas. This is a different probability of A and B than what we used in our formula yesterday. So in the 12.4 formula, this was the 12.4 formula that you had. This probability of A and B meant A and B happening at the same time. Like if I draw one card, what's the probability of a king and a red card or something like that? This probability of A and B are two separate things. So what's the probability of this happening and then that happening? Confusing. We'll work on it. So anyways, that's independent events. A dependent event is when the occurrence of one event does have an effect on the other event. And what I mean by that is, let's say that I was drawing cards. If I draw one card and then I don't put it in the back of the deck, when I draw my second card, now there's actually only 51 cards in the deck instead of 52. So that's considered dependent because now when I draw my second card, it'd be something out of 51 for the probability. Here's the formula for that one. Probability of A and B is equal to probability of A times, and then we have this weird symbol here, and I'll explain in a second. It's the probability of B, and that's a vertical line, A, close parentheses. That is called conditional probability. Conditional probability. It's really just the probability of B. Just it has a special symbol saying that since A already happened, probability of B is going to be slightly different now than it would have if A had not happened. Well, I'll say more in a little bit. Okay, so first let's just talk about how to find if something's independent or dependent. Remember, independent, the first event has no effect on the second event. Dependent, the first event does have an effect on the second event. So, two coins are tossed. If I've got one coin, does that outcome affect the outcome of the second coin? It doesn't. So that one is independent. I'm going to use an I instead of writing it all out. Part B, two cards are drawn from a standard deck. The first card is replaced before drawing the second card. So imagine me taking out a card, putting it back, shuffling it all up, then taking the second card. That would be independent then, because I put the card back before drawing a card. Now for part C, two cards are drawn from a standard deck. The first card is not replaced before drawing the second card. Those are dependent because now the second probability will change based off of what happened with the first probability. And by the way, this is called, when it is replaced, it's called with replacement. Sometimes you see it that way, and if it's not replaced, it's called without replacement. Okay, in D, in a survey, every person can answer yes or no. So what we're thinking of is, if one person answers yes, does that have an effect on what the second person answered? You could argue that maybe it will, but let's pretend like both of them, we don't know what the other person said. So we're going to say independent because what one person says should have no effect on the other person if they don't know who said what. Part E, you win the lottery. Does this have anything to do with your neighbor winning the lottery next week? I'd say in most cases not, unless it's something like the Powerball or something where it's cumulative with the tickets you get. And then last but not least, a child puts a quarter in the gumball machine, they get a red gumball. And now a second child is trying to get a gumball, maybe a red gumball. Now this one is dependent because once this first child takes a gumball out of the machine, there's less gumballs for the second child to pick from, so her probability or his probability is going to change. We're going to do these with actual numbers, so if you're feeling a little confused right now, keep listening. Example 2. We have a lot of different things we're going to do. We're not going to do all of them today in this video, but we always want to decide if it's dependent or independent as we're going along, and I'm going to say more about this in a little bit. I have this jar. It contains 12 red, 16 blue, and 18 white marbles. 3 marbles are chosen from the jar with replacement. So what that means is I take a marble out, I put it back. I draw another marble, I put it back, shuffle them up before drawing the third marble. What is the probability? None are white. So by the way, I counted this up. There's actually 46 total marbles. And when I gave you this formula, A and B are representing each marble draw, and I'm multiplying. So what I'm going to do is I'm going to find, and in this situation I've got 3 things I'm doing. So every marble draw I do gets its own fraction. So my first marble draw, that might be like the probability of A, there's 46 marbles to pick from. I want the non-white marbles. There's 28 that are not white. Now imagine this though, I took out the marble, I put it back in before drawing the next marble. So now I'm drawing a second marble, but there's still 28 out of 46 to choose from because I put it back. I put it back again, that means that's the with replacement part, and so there's 28 out of 46 again. For most of these, we're going to do the decimal, and we're going to do to 3 decimal places. If you're typing this all into your calculator, for a lot of your calculators you may need to use parentheses like this. In this case you could also do 28 over 46 cubed because there's 3 of them, and you should end up with 0.226. If you want to pause the video and try typing it in, that would be good if you have time. Question: were these different marble draws independent of each other, or were they dependent of each other? And here's how we know. If this probability didn't change at all from the first one, it's independent. So I put the marble back, so when I made my second marble draw, it wasn't affected by the first one. So that's independent. Okay. Part B. Now same jar, 12 red, 16 blue, 18 white. 2 marbles are drawn, so this time I'm only going to have 2 fractions. So again, multiple card draws or multiple marbles means multiple fractions. You have 1 fraction for each event that's happening. So I've got 2 events because I have 2 marbles. Again with replacement, so it's going to be independent. What's the probability? You'll choose a red and then a blue. Okay, so on the first draw, I want to choose a red. There's still 46 to choose from. There are 12 red ones. With replacement means I put it back before I take the next one. So on my second draw, there's 46 marbles still, but there are 16 blue ones. And when you multiply those together, you should get approximately 0.091. For part C, it actually is going to be without replacement, so this one's going to be a dependent, and I'll show you what happens here. So same marble draw, I'm going to choose 3 marbles. I want the probability none are white. So 3 marbles are chosen without the replacement. What is the probability? None are white. Without replacement means I take it out, I do not put it back. So these are going to be dependent events. Here's how this works. 3 marble draws. So I got 3, so I'm going to have 3 fractions. The first marble I draw, I want a not white marble. There's 28 not white marbles. There's 46 total marbles. You always assume you got what you wanted when you're doing probability. So now I have my second marble draw, but there's only 27 not white marbles, and there's only 45 marbles total, because I took one out. This is what it means by dependent. This number is now different, and especially the bottom number is different because the first one happened. That's what dependent means if I'm applying it to a situation here. On my third marble draw, now there's only 26 left, and there's only 44 total marbles. And I end up with 0.216 for my answer for that. And sometimes we're going to do something one step harder. Well, not really. We're going to use the complement that we learned about in 12.4. So same jar of marbles, what's the probability at least 1 marble is white when 3 are chosen? So what this means is I want 1 marble being white, 2 marbles being white, or 3 marbles being white. And I want to show you something really quick that you do not have to write down. When I'm drawing these 3 marbles, I could either have none white, I could have 1 white, I could have 2 whites, 2 white marbles, or I could have 3 white marbles. And if I found all of those probabilities, that would add up to 100%, because those are the only 4 things that could possibly happen with my trying to get a white marble when I'm drawing 3 marbles. So those are the only things that could happen. Now if I want at least 1, what I want is I want to find the probability of 1 white marble plus the probability of 2 white marbles plus the probability of 3 white marbles. Now the thing is, if I do it like that, it takes longer, and it's also actually a more complicated problem than we're ever going to learn in this class, because there's something we would have to do with combinations to make this, to get the correct answer. So whenever I have a situation like this with the at least 1, you might want to like star, star, star that. Whenever I have that at least 1, and we'll do a few examples like it as we go through here, I'm going to actually find the complement. So what I'm going to do, in order to find this, I'm going to do 1 subtract what I don't want, and I will get the correct answer. So I'm going to do 1 subtract the probability of getting no white marbles. This part, why don't you write down? So again, I'm doing 1 subtract what I don't want, and when I subtract off what I don't want, I'll get the answer for what I want. This is the way you need to do this problem in this class. There is an alternate method, but we're not going to learn it because it is quite tricky. And the probability of having no white marbles, that's what we just found in example C. And they're also often going to do that to you to try to kind of make it a little easier. So I'm going to do 1 minus a 0.216, and I end up with 0.784. So there's a 0.784%, or not percent, but 0.784 or 78.4% chance I'm not going to get, or I'm going to get at least 1 white marble. This is also a dependent event because it's matching with this situation up here. And we'll say more about that in a little bit. I'm just going to do 2 more examples for this video. Let's look at example E. During the 1997 baseball season, Florida Marlins won 5 out of 7 home games, 3 out of 7 away games against the San Francisco Giants. Okay, so during 1997 now, they're going to play 2 games for the next series. They're going to play 2 games at home and then the 3rd game away. The Marlins did end up winning all 3 games, but our question is, what was the probability of that happening? And we can use what previously happened as our probability. So what they want us to do is they want us to win at home. They want us to win at home again. And then they want us to win away. And so those are the 3 probabilities I'm going to find and multiply them together in 3 events, so 3 fractions. We have to decide if these are independent or dependent. Now, if you know baseball, it could be a dependent event because there could be a mental aspect of the game going on, or maybe players get injured or whatnot. But we don't have any of that information. This is the only information we have, and it doesn't tell us anything about, you know, like if the first game is won, then they have a this % chance of blah, blah, blah. We just have this, nothing else. So it's going to be an independent event because these are the only two fractions I'm given here. The probability of winning at home was 5 out of 7, and we'll just assume it's the same each time then. The probability of winning away is 3 out of 7. So this time, they actually just gave us the 3 fractions. We didn't have to even do any counting. And you get 0.219. One more, part F. 2 integers, 0 through 9, are chosen by a random number generator on a computer. So basically, it's just going to randomly spit out a number between 0 and 9. And it's 2 of them are going to be drawn. So I'm going to have 2 fractions. It says, what's the probability of choosing the number 2 both times? Okay, so my possibilities are 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So there's actually 10 possible numbers. We want the probability of drawing the number 2. Now there's only one number that is 2, so we're going to have 1 out of 10. So there's 1 out of 10 chance that that's going to spit out a number 2. And the whole point of it being random number generator is that it's an independent event. It doesn't matter what they spit out the first time, the second time you still got the same probability. So that one ends up being 0.01. Thanks for listening, and we'll catch you again with another video for the second part, or we'll do it in class. Have a great night.